Hi, and welcome to this section of the Calculus 1 Extra Help with Derivatives DVD course. In this entire DVD course, what we're going to do is zero in on one of the core principles of calculus that everyone deals with, and that is how to properly take derivatives. So what we're going to do is really zoom in on that topic, which covers about the first half of Calculus 1, and we'll really work a lot of problems to give you not only the skills by seeing them worked and the repository of problems so that you'll understand how to do your homework, but also it'll serve as sort of like a vault of problems that are already worked for you so that when you're doing your homework or you're prepping for an exam, simply by going through this DVD course, you'll have a vault of pre-worked problems that are the representative problems that you'll probably be asked to do on your test. So it's a great way to learn how to do this stuff, but it's also a great way to review for exams and tests. So that's basically what I'm trying to say here. Now, I want to go ahead and say right up front that I already have a Calculus 1 tutor out there on the market, and it's a phenomenal course. It's one of the most popular DVD courses that we have, and it's being used around the world and in universities and high schools and in libraries, and it's a course that I've gotten amazing feedback from over the last few years that it's been out. And basically a really good primer and tutorial on Calculus 1 that you'll typically see at the university level or at the high school level, at the AP level. This guy, I've gotten a lot of student requests over the years to give extra help and extra problems with really getting down how to take derivatives. Now, this material is covered in the Calculus 1 tutor, so I really do encourage you, if you don't already have it, to please go over to that disc and watch that disc first, at least the part about derivatives, because there's a lot of background info and a lot of really great problems in that disc. But what we're going to do in this course is take that one topic, which is about half of Calculus 1, and zoom in on it and work just a lot of problems of different types, a lot more problems that I was able to put on that first DVD disc. So you can kind of think of that one as sort of the parent. It gives you the general idea of Calculus 1, gives you lots of examples, good solid framework. This guy is like the in-depth practice for your test, practice for your homework, extra problems to sharpen your skills. And that's the only way you get good at this stuff, is by sharpening those skills and working problems. So that's what we're going to do here. So what I want to do first, briefly, since this is a tutorial on derivatives, is I want to give you another primer, real basic overview of what a derivative is. I did that in the other course, the Calculus 1 tutor. Go watch that, definitely a good deal. I'm going to do it here in slightly different fashion, just so that you'll have another review of what a derivative is before we start to get into the differentiation methods. And every section from here on out in this course is going to contain a new different derivative method, and by the end of it you should feel really comfortable taking derivatives of pretty much any function you can think of. So with that, let's get started. So what we're going to do is talk about a derivative. In your calculus book that you might be using in class, derivative is always introduced in terms of a limit, because it's really what it is. It's a limit, and I covered that definition in the other DVD course just mentioned, Calculus 1 tutor. I'm not going to go into that definition of a derivative because you can see it in your book and you can also see it in the other course. But what I want to focus on here is sort of the practical meaning of the derivative. What does it mean? How is it useful? Because that is what's going to be most important as you go through calculus and on into physics and other courses that you really use these things. The bottom line is, a derivative is telling you how fast something changes. And I want to say that one more time because it's really important. A derivative is telling you how fast something is changing, right? So we deal with change every day. You know, when we go 35 miles per hour or kilometers per hour down the road, that's the rate of change of our distance with respect to time. So we're talking about the rate of change. If we're looking at the temperature dropping outside, the temperature's dropping, 3 degrees Celsius per hour. That's the rate of change of the temperature with respect to time, right? So we're looking at how something is changing, but compared to time usually. Could be compared to whatever, just depending on the meaning of it, but it's always going to be compared to something. So meters per second compared to time. Celsius per minute or per second is with respect to time. We're looking at the rate of change of something with respect to time. So you can always think of it in that terms, and that is really the practical definition. If you think about it in a little more mathematical terms, we always learn about functions, right? Which could represent anything at all. So we have a function here in a coordinate plane, and it's got a squiggly nature to it. Maybe it's a straight line, maybe it's a parabola. Well, you can sort of look at that and realize that at any given point on that function, it's going to have a certain, we call it a rate of change, which means how steep is the thing? How fast is that function really changing? The way we represent that in math is the slope of that function. So the bottom line, without writing anything at all on the board, is a derivative is telling you how fast your function is changing, right? And so when we plot a function, we usually talk about the slope of that function at a certain point. How fast or how steep is that slope? That means how fast is that function changing, really? So when we take derivatives, that's all we're doing, is we're looking at a function, we take its derivative, and that derivative tells us how fast that function is changing, right? So it has practical applications everywhere. I just gave you one because, meters per second is how fast the position is changing with respect to time. So that's a derivative, really. So velocity is a derivative of position. That's one of the first things you learn in physics. So that's enough talking for now. I want to write something on the board and try to make this a little bit more concrete for you. So let's just briefly review the concept of a derivative without too much heartache. So if I have a coordinate system here, I'll just go ahead and make it blue. So let's say I've got, just draw any old function here, like this. So here you have x, and here you have y, or you could just call it f of x. So let's go ahead and do that. Usually in calculus class, you refer to everything in terms of a function f of x. All right, so this guy is any old function. We could have any old function we want. Could have a straight line, could have a squiggly, function, whatever. But just for the sake of talking about it, let's draw a nice parabola down here because almost everybody understands really what a parabola is. So if this is a parabola, then this f of x is x squared, let's say. That's the parabola that we're talking about in this case. So it goes down to the origin, comes back up. As you go farther to the right over here, it gets steeper and steeper and steeper up this direction. If you go negative, it gets steeper and steeper and steeper up this direction. So notice I use the word steeper. What do I mean when I say that? Something is more steep. It means it has a higher slope, right? So I guess what I'm trying to say is if you look at this function, if you look at this point right here, how would you represent how steep this function, how fast that function changes at this point? How would you represent that? Just graphically, forgetting about calculus for a second. Well, what you would do is you would look at this function, and if you're going to try to represent how fast it changes, the only way you can really do it is to draw a line, because the function's totally curved the whole direction, right? It's curved every single point, so it's not a straight line. So what we do is we draw a line tangent, is what we say, to this curve. Now what we mean is that line comes right up on top of that curve. It touches the curve at only one point, okay, which is the point that I have the big dot here. Everywhere else it doesn't quite touch it. It gets really, really close. We call that a tangent line. It's just a line that comes right up to that graph, but it only intersects it at that one and only one point there. And everywhere else it kind of comes slowly away from the guy. So if we were going to say that this point, if we draw this line tangent to it, then all we have to do at that point is use algebra to figure out what is the slope of this line. And we get a number. And that number is what we really refer to as the derivative of this function at this point. It's the slope of this function at this point. So basically, derivative is the slope of the line tangent to this curve. And we're going to learn in this course how to actually take this function and take its derivative mathematically. Right now, we're just doing graphical stuff. So really, just in terms of words, we're going to say this is high slope. Why do we say it's high slope? Because it's pretty steep here. You see, as we go farther and farther, this curve is going to go more and more vertical. And if you remember back from algebra, more and more vertical is like a mountain, a vertical mountain, really, really steep. Really shallow mountain, right, like a very slow hill, is very shallow, so not so steep. So we would say that we have a higher slope of this curve here, which is the slope of the line tangent, which means the derivative is larger also, basically. Let's look at a different point. What about this point down here? I think everyone would agree that this derivative, which is the slope of the line tangent down here, if we were to draw this tangent line, which goes right through, just doing the best I can to make it like that, but it goes right through and touches only at one point, that the slope of this line tangent here is lower. So I'll put lower slope. Why we say it's lower slope or smaller slope? It's because this guy was very steep. This guy is more shallow. So we say it has a lower slope, which means that at this point, the derivative of this function is lower. That's all it means. The slope is lower. The only way you can define slope with these curved functions is draw a line tangent because the thing is changing. It's curved all the time. Now, what do you think is going to happen right at the bottom? If we look right at x is equal to 0 and y is equal to 0. If we draw a line tangent to that, what's going to happen is it's going to intersect like this. It's going to be a flat horizontal line. What is the slope of a horizontal line? Well, the slope is 0. So this slope is 0. 0 slope. That's this guy right here. So I'll put a little arrow right there. 0 slope. So what does that mean? It means the derivative is 0. So the rate of change, how fast this function is changing with respect to time, or with respect to x actually, so how fast the function is changing in this direction with respect to this direction, we call it its derivative, is the slope of the line tangent to the function, and in this case it's 0. It's simply because we draw the line and it has a 0 slope, that's the reason. So we can go off in the negative direction and we can put a line here, and we can do our best to draw a tangent line to that, and we could do a line up here again just for completeness and try to draw a line tangent to that. And I think after that following discussion, you could see this is probably lower slope right here, and this is high slope. So as we go more and more negative, we're going to get back into the high slope territory. But the only difference between this and this, when you really think about it, is the following. Let me go ahead and draw right here. So let me put a little curly bracket from here on out here. All this function over here on the right hand side, this is positive slope, which means that every one of these things that we've drawn, this is a positive slope. This is a positive slope. Think back to your algebra, right? Any slope that's slanted this direction is positive by definition. Rise over run. That's all I'm saying here. If it's sloped in the other direction, rise over run is going to end up being negative. So this is a negative slope. Any slope going catty corner like this is negative. Any slope going like this is positive. So all of the slopes over here is negative. Negative slope. So congratulations, we haven't actually taken a derivative yet. I haven't shown you how to mathematically take x squared and calculate its derivative, but we've talked graphically that if we draw a simple curved function on the board, x squared, that basically you've learned that its derivative is high and positive over here because it's steep and it's pointing in this direction. The derivative here is a little bit lower, but it's still positive over here. The derivative right at the apex, or the lowest point of the function, the negative apex really, is right down here. It's exactly 0 slope, so that means its derivative is 0 at this point. And over here, as we go this direction, the derivative again gets higher and higher and higher and higher, but in the negative direction. So the derivative is basically negative as we get over here, negative and getting larger, larger in the negative sense as we go that way. So what I would like to do now is, we've talked about conceptually what the derivative is doing as we get higher and steeper and so on. And now what I want to do is draw another coordinate axis, really, right below it. And let's go ahead and graph the derivative. I'm not even going to tell you how we arrived at that derivative. We'll learn that in a second. But I'm just going to tell you ahead of time. Let me draw an axis right below. Okay, so this is going to be x, and this is going to be f of x. Right here. So what I'd like to do now, with no proof at all, is to basically draw the derivative of this curve and show you how it represents exactly what we've been talking about up here. So let's do that right now. The derivative of this function x squared, and I'll show you how to do this in a moment mathematically, but just trust me for a minute. The derivative of this function, f of x, we call it f prime of x. It just means taking the derivative of this function. And the answer is 2 times x. Okay, we'll show you how to do that here in a little bit. The actual graph of 2x, if you can think about it for a second, if it were f of x is equal to x, or if the derivative was equal to just x, it would be a line that would go just like this, splitting it by basically 45 degrees, like this. Since it's 2x, it's a little bit steeper, so it's a little bit more like that. So let me switch colors here and draw the derivative. So if you can think of if it were just x, it'd be like this. So 2x is something more or less like this. And it's not an exact drawing. That's being exact is not the point here. And showing you the general trend is important. So if you look at the straight line that's a little bit steeper than a typical one at y is equal to x, that's the graph of our derivative. So this is what we call the first derivative of this function f of x. And if you look at it, what I'm trying to tell you is this function, this one here, the derivative, really does represent the slope or the steepness of the original function we had at every single point. And if you think about that, look right here at the origin. Let me switch colors here. What is the value of this derivative right here at the origin? Well, it's 0. At x is equal to 0, we say the derivative is equal to 0. So that means the slope of the original curve is 0 at that point, and that's exactly what we have said is the case. So we drew it graphically by a tangent line showing you the slope of this line is 0 there, and the derivative was 0, but graphically this is a graph of the derivative. If you look at the same point, the derivative is 0, so the slope of the original function is 0, right? So let me go ahead and just put a little reminder to yourself, this is 0, 0, right? Now if we go up in the positive sense, then as we move along this direction along x, we're getting to larger and larger values, but it's along a line, right? So this is a value of some slope. This is a higher value. This is a higher value as we go more and more. It's exactly the same thing as what we've seen here. As we go off to the right, this is a kind of an intermediate slope. This is higher, and as we go more and more and more, we get to higher and higher slopes. We're seeing exactly the same thing. So somewhere like, maybe like here, this may be lower. Lower slope of the original curve is what I'm trying to say. This guy up here may be higher because it physically represents as we go farther along x, we're getting to larger and larger values of the derivative. As we go farther along x, we're getting to larger and larger values of the slope. Okay? So that's what we're seeing here. Now if we go in the other sense, if we go the other direction, then this is going to be, we'll call it lower again. But in this case, it's negative. Everything begins to be negative on this side, and this is higher, but again in the negative direction. So the derivative represents exactly what we have here. Here was the 0 slope. As we went this direction, we got to higher and higher slopes, but in the negative sense because the tangent line was going in the negative direction. So really make sure that you truly understand what this derivative graph is really representing. We take a function x squared, we calculate its derivative, and we plot it, and we'll show you how. That's the whole purpose of this course, how to calculate these derivatives, right? When you plot the derivative directly underneath your original curve, this derivative should represent the slope of the original curve at every single point. So you should be able to look at the derivative and say quickly, okay, my original function is steeper here because my derivative's higher. My original function should be steeper in the other direction down here because it's negative. When a derivative is negative, it means the slope of the original function is negative, exactly as we've shown with the tangent lines here. And right here we have a crossing. So at this exact moment, the derivative is what we call 0, which means the slope of our original function is 0. So that is sort of a 5-minute, or maybe a 10-minute preview of really what derivatives are. They're functions that you derive, right? Derivative. You take a derivative of the first function, you take the function, you derive its derivative from it. That derivative function then basically represents sort of the slope of the original function at all the different points. I can put any point I want in here for x. I can put x is equal to 95 way over here, and I'll get a value of the slope of the original function, right? So this is exactly what a derivative is. Now let me show you briefly a little bit of notation before we start calculating a lot of derivatives. If we have a function f of x, which is typically what you'll see in a calculus book, then we call the first derivative means we take a derivative one time, and here we get it. First derivative. We can really represent it two ways. One way is we say f prime of x. So what this means is we're taking f of x. This prime just simply means it's the first derivative because there's only one prime here. We'll talk about higher derivatives a little bit later, but just for now, for the time being, just know that you can continue taking derivatives over and over again, so you can get to a second derivative and a third derivative and a fourth derivative. But for now, it's really not that important. We just take the first derivative, so we have one little mark there. Another way to write it would be to write it this way: df with a fraction like this, and then dx. So the way you say this is the derivative of the function f with respect to x. So we would say that f prime of x is, in this case, f prime of x we said was 2x, so we write it as 2x, or we could say df with respect to x is 2x. These two things are saying exactly the same thing. And in fact, as we go through the course calculating derivatives, I'm going to frequently switch back and forth between notations. This is sort of like a more compact way of writing things. It's easier to write down in your paper. You're doing problems and homework than writing this guy down. But this has some advantages and some other stuff that we'll talk about a little bit later. It'll make it a little easier for you to understand what's going on in some cases. So just get in the habit of saying, when you see this, it's the derivative of this function with respect to x. When you see this, it's the derivative of a function with respect to how x is changing. In both cases, it's exactly the same thing. It's telling you the slope of the original function at any point you want to evaluate it at. You can plug in any point you want. All right, now what we need to do is start taking some derivatives and showing you how to go from one function to its first derivative. So what we're going to do is take things slow and give you the introductory kind of basic rules for differentiation is what we call it. And you'll find really that it's not that hard, but what you have to do is really build your skills up. A lot of students, they'll read all the rules of taking derivatives and they think they get it. Okay, there's 5 or 6 rules of taking derivative. I got it. They go take a test and they bomb it because you really have to practice. It's like working with fractions. You might know how to add fractions, but you really have to start dealing with improper fractions and mixed fractions and negative fractions. Build your skills. Otherwise, you just think you know something you really don't know at all. So that's what we're going to do now. What I'm going to do right here at the top of this board is I'm going to write down a few simple rules of taking derivatives, the most basic ones. And then we're going to work a whole slew of problems dealing with just those rules. And as we go to the next section, I'll introduce a new rule each time that kind of makes it possible for you to take more and more complicated derivatives. By the end of the course, you'll be absolutely fluent in taking any derivative that a professor might throw at you. All right, so let's go ahead and do that now. And what we want to do is just kind of write down a few things. First thing is, if I have a function, f of x, and that function is just equal to a constant c. So that's c means constant. What I mean by a constant is c could be 5, c could be 7, c could be negative 2.4, c could be 0. It doesn't matter. It's a constant. It's just a number. If this function is just a number, then we say that its derivative, f prime of x, the derivative, the slope of this guy really, is just equal to 0. It's always the case, no matter what constant you have. If your function is f of x is equal to 10, then its derivative is 0. If f of x is equal to 19.4, then its first derivative is 0. Always the case. Negative, positive, decimal fraction, doesn't matter. Any constant derivative is always, derivative of that guy is always 0. And if you think about it, it makes sense because how would you graph this guy? How would you graph this function? F of x is equal to a constant. Well, you draw your little axes and you have a horizontal line. That's what that graph looks like at the value of whatever your constant is. So putting 2 and 2 together, if a derivative is really the slope of your function, then what is the slope of a horizontal line? Because this is just going to be a horizontal line. The slope of any horizontal line is always 0. So the derivative is always 0. So everything I'm telling you is totally consistent. Not making new rules up. It's really something you could have probably thought about on your own, but in your calculus book, you'll typically have something written that looks something at least similar to that. So first rule, if your function is simply a constant, its derivative is just 0. Next rule. If I have some function like this, x to the power of n, where n is a number, so this could be x to the 5th, x to the 6th, x to the 19th, whatever, then what you're going to do is f prime of x, the first derivative is going to be equal to, you take your exponent, you stick it out in front, and then you write x, and then the new exponent that you have here is n minus 1. So literally, if you have x to the power of whatever, x to the power of 3, x to the power of 5, whatever, you just take your exponent, stick it in front, put x again, and then your new exponent is the same exponent you started with, but you just subtract 1. That works for any exponent. Now, x to the 19th, x to the negative 7, x to the 2.4, x to the 1/2, doesn't matter. Whatever your exponent is, you just subtract 1. And you just stick the original exponent right in front. Now, why does this work? Why does this always give you the slope of the original curve that you started with. Well, truthfully, that's outside the scope of what I want to talk to you about. You can go in your calculus book and probably even a more advanced calculus book than what you have, and you can go really read the theory of how Newton and Leibniz and these really famous mathematicians from a couple hundred years ago, how they invented calculus. And there are lengthy proofs to prove to people that this really and truly is the derivative. It does represent the slope of this original curve at all points. But the proof of that is really beyond the scope of what I want to talk to you about, because at heart, what I'm interested in is teaching you how to solve problems. It's very worthwhile to go look at that stuff if you're interested in it. But, you know, a lot of times in math, you learn what other people have done, and you take it as fact that has been proven. And as you learn more and more, you might go back and revisit these things and learn why it was proven that way. But it's kind of akin to, you know, pi r squared. Area of a circle is pi r squared. Why is that true? Well, that's proven too. You can go prove that. You can certainly take a circle and measure it and prove it's true, but there are other ways to prove that it's true. Why is the area of a triangle, you know, what we know to be true? Why is the area of a square what we know to be true? Well, there are proofs to those things that you can go figure out. Same thing here. There is a proof to this that you could go figure out, but to be honest with you, it's just going to bog down the discussion. So what I really want to impress upon you is that this is fact. This is proven by Newton, Leibniz, and these other people that invented calculus. If you're interested in that, great, go read about it. But really, it's not necessary to be able to take derivatives till you're blue in the face and really understand how to use them, which is what I'm mostly interested in. So if this looks a little bit weird, you don't worry. We're going to do, you know, tons of problems. It'll be absolutely clear. Next thing I want to talk to you about. What if I have a function, f, and out in front of that function I have a constant, right? And I want to take the derivative of this combination. So what if I have, you know, well, we'll get to some examples in a minute, but the function can be anything. The function can be x squared, could be 2x, whatever. And in front of this guy I have just a number like 2. Well, the way you take its derivative is you simply take this constant out, and then I take the derivative of my function any way that I know how. And I'm teaching you step by step how to do this. So if you have a function that you know how to take its derivative of, go ahead and take it. If it has a constant sitting right out in front of the function and you're taking the derivative of the whole thing, you just take that constant and stick it in front of the answer that you get for your derivative. And we'll get some examples here in just a second. Now, final thing we're going to talk about before we start working some problems. What if I have two different functions, like, let's call it f of x plus g of x. And I want to take the derivative of the combination. This might be x squared plus, and this might be 2x. This might be sine plus cosine. This might be, you know, 1/2 x plus x to the negative 3. Two different functions. No matter what, to take the derivative of the sum of two or more different functions, you just simply take the functions of the derivatives of the individual functions and just add them together. Right? So this is it. These are the four that I want you to kind of have in your head for this section. And all of the problems that we're going to work here in just a minute are going to use all four of these guys. As we go in section to section in the future, we'll expand and give you a few more rules in different cases, really, and show you how to handle. But right now, all we need to know is the following. If you have a function that's simply equal to a number, its derivative is always 0. If you have a function that's x raised to a power of some number, then you just take the exponent down, write x, and then subtract 1 off the exponent. That's easy. If you have a function multiplied by a constant, you just take the constant outside and then take the derivative of the function that you had on the inside there. So the constant basically moves out. And if you have the sum of two functions that you're taking the derivative of, you just take the derivative of each individual function separately and then add the results together. This bottom one actually works for any number. I mean, you might have 6 things added together that you would then take a derivative of, and you just take the derivative of each little part and add them together. So this, think of a polynomial, right? 3x squared plus 2x plus, 3 or something like that. So you might have 3 terms. You might have 10 terms if it's a really large polynomial. Well, all you do is you take the derivative of each little part and add them up. That's really all this is saying. So what we're going to do now is we're going to work a lot of problems, because with derivatives, and with actually all math, it all seems a little more difficult when you write this stuff down. This is what you'd see in a book. The reason I'm presenting this is only because you're going to see it in your book. A lot of students read it, get upset, get worried, but trust me, this is something that my little sister can do, and she's not even taking calculus. You'll see in just a second. Let's do the first problem. Let's say you have a very simple function. F of x is equal to x to the 4th power. So how do you take the derivative of this guy? Well, I'm telling you that I've already told you everything you need to know. So you go back up here and you say, well, this guy applies. It's x raised to some power. So all I do to take the derivative is I take the exponent and I write it out in front, and then I write down x, and then for my new exponent, I take my original exponent and subtract 1. So f prime of x is equal to 4x to the 3rd power. 4x to the 3rd power. And that, ladies and gentlemen, is the answer. That's all you need to know. So it follows exactly what we said. We take the exponent down, write x, exponent minus 1. That's all we do. This is going to become so incredibly commonplace for you in Calculus 1 that you won't even think about, matching it up with a rule. I mean, anytime you see a polynomial term like this, or an exponential term, or an x to the nth term like this, you'll know exactly how to take the derivative. So this was pretty simple. You take the exponent down, write x, subtract 1 off of the top. Let's go to one very similar. What if you have f of x is x to the power of 5? How would you do that? Same thing. You take the exponent down like this, then you write x, and you just subtract 1 off of the top. So it's going to be to the 4th power. 5x to the 4th power, and that is the answer. Okay, now let's do something, we'll switch colors just because. We'll do something similar. Let's say we have f of x is equal to x squared plus x. Now, we know how to take the derivative of x squared because it's really similar to what we've been doing in the first two problems. We know how to take the derivative of x because really that's x to the 1st power, so we know how to take the derivative of this and this. So notice that since they're added together, we're taking the derivative of the whole thing. All we do is we take the derivative of each part and just add them together. So we already know how to do this, even though it looks more complicated than these, because we just take the derivative of each little part separately and then add it together. So f prime of x is equal to, what are we going to get for the first guy? We take the exponent down, 2, write x, and then for our exponent here, it's going to be to the 1st power. 2 minus 1 is 1, so we leave a 1 here. All right? Plus, what about this guy? Well, we have an implied 1 in the exponent, so a 1 comes down, right? So just to be totally clear, let me go ahead and write it all out. So we have a 1 coming down, and then we have an x, and then the exponent is going to be 1 minus 1. Because our original exponent is 1, we always subtract 1 off of the exponent. Well, this is x to the 0 power. And what is anything to the 0 power when you think about it? Anything to the 0 power is always 1. Even x to the 0 power is always 1. So really the final answer here, f prime of x, is equal to 2x plus 1. 2x plus 1. And that's the final answer. And you will just get used to seeing this a lot whenever you get these guys. When you're taking the derivative of x, you'll just you'll get so used to it that you'll know the answer is 1 without even thinking about this stuff. But just to make it absolutely clear, for the first guy, the 2 comes down, x, 2 minus 1 gives us 1 for this exponent. For this guy, 1 comes down, then times x, and then for the exponent, the new exponent is 1 minus 1, which is 0, which means x to the 0 is 1. So basically, this part disappears. We're left with just simply the 1, 2x plus 1. Now, I hope you can see that these things, this is not rocket science, really. I mean, once I show you how to do it, I could have skipped all this, really, if I wanted to, and just showed you by doing it here. But it's important that you tie it back to your rules, because when you're studying for your test and you're just reading your book, you really need to understand what they're saying. So I'm trying to show you through examples that this complicated looking stuff that we see up here is really, really quite simple. And as we go farther, we're going to take more and more complicated derivatives of different cases, and we're going to find out that by and large the process is really, the nice thing about derivatives, the process is very bulletproof. Once you know how to do